previously looked at reversible reactions, equilibria, and Le Chatelier's principle. What we're going to look at today is one specific instance of that. So the Haber process is a way of making ammonia. Ammonia is a very useful chemical. It has the formula NH3. It is used to make artificial fertilizers. The raw materials for making ammonia are nitrogen and hydrogen. Nitrogen doesn't react very well with hydrogen under normal conditions because nitrogen is very, very unreactive. It is inert. So you have to do some special conditions in order to make it react with the hydrogen. The overall reaction looks like this. As you can see, it is a reversible reaction. So this is the balanced version here. The nitrogen used to make ammonia in the Haber process comes from the fractional distillation of liquid air. In the exam, when you're asked where it comes from, use that whole phrase. There's usually a couple of marks for that. So the fractional distillation of liquid air. Hydrogen, they get the hydrogen not from the air. Hydrogen doesn't come from the air. Hydrogen comes from fossil fuels. It comes specifically from natural gas. So hydrogen from natural gas, nitrogen from the fractional distillation of liquid air. When they react together, they'll only react together, well, they won't react together very much. You have to think about it as a reversible reaction. You want to move that position of equilibrium further to the right. We want to make more ammonia, as much ammonia as possible. And that is called increasing the yield. Increasing the yield makes more ammonia. So the conditions for the Haber process, you have to memorize these. You'll be expected to memorize these on the exam. The conditions are an iron catalyst, 450 degrees Celsius, and 200 atmospheres. You have to give the specific numbers. You can't just say high temperature, high pressure, anything like that. It has to be 450 degrees Celsius and 200 atmospheres of pressure. Why are all of those conditions chosen? Let's have a look at them one by one. Well, the iron is a catalyst. The iron is not going to have any effect on the position of equilibrium. It's not going to change the position of equilibrium. Catalysts don't do that. What the iron does is speed up the rate of reaction, like all catalysts. So number one, the iron speeds up the rate of reaction. Has no effect on the position of the equilibrium. Has no effect on the yield. Second one there, temperature. The forwards reaction in the Haber process is exothermic. If we think about Le Chatelier's principle, then if the forward reaction is exothermic, increasing the temperature is going to do the opposite. It is going to do the backwards reaction. It's going to move the position of equilibrium to the left. It is actually going to decrease the yield. So increasing the temperature decreases the yield. So why is 450 degrees Celsius chosen? Well, if we had a very low temperature, we would increase the yield. But it would be too slow. So 450 degrees Celsius is a compromise between the yield and the rate. Increasing the temperature would favor the forward reaction and favor the backward reaction and decrease the yield. Decreasing the temperature, so make it colder, would favor the forward reaction and increase the yield. But we don't use a very high temperature. 450 is still high, but we don't use a very high temperature because it is a compromise between yield and rate. Pressure. Le Chatelier's principle tells us that if we increase the pressure, we favor the side, or we move the position of equilibrium towards the side with the fewest moles of gas, or the fewest molecules. As we can see from this equation, on the right hand side has fewer molecules than the left hand side. So increasing the pressure is going to increase the yield. It moves the position to the right. It is also going to increase the rate because increasing pressure increases rate of reaction. So we want to use as high a pressure as we can. Why do we stop at 200 atmospheres? Because if it goes any higher, high pressures are expensive. They cost a lot of money for specialized equipment, and they are unsafe. So the pressure chosen is 200 atmospheres because that is a trade-off between a high yield and safety or cost. Okay. So that's the conditions for the Haber process. You have to memorize those. Now, at these conditions, the yield is only around 15%. So about 15% of the nitrogen and hydrogen gets changed into ammonia. How do we remove the ammonia from the gases? Well, ammonia, if you cool it down, ammonia will condense first. It has a higher condensation point or boiling point. So it has a higher boiling point. So if we cool it down, ammonia will condense into a liquid. We can then open a tap, take the ammonia out, and you leave behind the hydrogen and nitrogen. 15% is quite a low yield, but that's not actually too much of a problem, because what you can then do is the unreacted gases can be recycled. You get another 15% and another 15%. So sum up the Haber process. You need to know the conditions. You need to know the reasons for the conditions chosen. You need to know how to remove the ammonia. You need to know where to get the raw materials from. And you need to know that the unreacted gases are recycled. Okay. All right. Thanks for watching.